All right, so this last assignment or activity for the data collection project called confidence intervals is going to have you access your daily data and apply confidence intervals where appropriate. So this is probably the trickiest thing that you're going to have to do, and it involves you having an idea of what kind of data you're working with. And all the work that we've done up until this point is going to help us make that determination. First thing I would ask you to think about is whether you believe that your first variable causes a change in your second variable. If that's the case, then you're going to want to do a regression analysis, right? Which we've already done, so all that stuff is down here. But we'll also want to do a linear correlation confidence interval. In addition, we need to do a confidence interval within each data set and between, right? So our choices are, just kind of going back to the activities that we've done, a confidence interval with sigma unknown, match pairs confidence interval, independent samples confidence interval, and a linear correlation, which I've already discussed. All right, so we'll start off by first creating a tab called CIs, confidence intervals, blank spreadsheet. I'm going to pull over some of the stuff from my confidence intervals means with sigma unknown spreadsheet, which really is just this stuff here. It's formatted slightly differently depending on which activity you're working with, but essentially it's the same structure. All right, we need multiple confidence levels. So what I would recommend is copy this over, give it a label. I'm going to put this here, I'll paste it right in that cell 3, A3, and I'm just going to pull the title, confidence interval, sigma unknown. I'll just pop that in here. All right. Now, just bear in mind, again, formatting is what it is. We'll have to be careful about that. But we do have two variables that we're working with. All right, so we'll have to do this process twice. All right, so I'm going to clean this up a little bit, maybe change the formatting. We want the high bound, the low bound, and then a conclusion. And if you like the way it's formatted in one of the other ones better, I think probably the most concise way, that could be a good one. But the way I had it for the correlation one might be more to your liking. You can just grab, wholesale, grab these and paste it in. That's fine too. I'm just going to take what I have here and edit it. All right, so we need to do a 0.10. That's a 2, not a 1. That's not even a 0. Okay. A low bound and a conclusion. Low bound, high bound, and conclusion. All right. I'm just going to wipe this out. Basically, I just needed the terms here to get it going. Then we'll do copy, paste, and paste. You can space it out however it makes sense to you to do it. 0.05. And the last one's 0.01. All right. Now again, we got to bear in mind that in my all data, I have high temperatures and low temperatures. So this analysis I'm going to do for highs and lows. So I'm going to take all this stuff and duplicate it to the right. Oh, I needed this stuff too. All right. I'm going to actually... Oops. No, I don't want to merge them. I want to unmerge them. Okay. Well, good enough. So we need these values of sample mean, sample standard deviation, the mean of the sample means, and the standard error. All right. So all that information. Let me create a new space here, insert one column to the left. Just kind of resize to make it look a little nicer. So let me get some yellow going here. Alright, I'm just going to resize, just aesthetics. Alright, so the sample mean equals average then we got to go into all data. We want the average. It's stored in our, the average is stored in our all data if you want to access it that way, but I'll just do it this way in case you forgot. All right, so that's the mean, standard deviation for the sample. Again, go into the tab, grab all the values, lock it in. The mean of the sample means is equal to the population mean, but these two numbers will be the same, right? And the standard error is this number divided by the square root of however many values there are in this set. So equals this divided by the square root of the number of values in the set. So count. If you happen to know the number off the top of your head, you can do that, but just copying down the line gets the job done too, as long as you have the count enabled. Oops, overshot the mark. Come on, one more, there we go. All right, so close that up. And now I have my standard error. Confidence level first off is 90, and we want 95. Then 99. Could have put those in earlier. All right, so this is a t interval, so equals. Now we will need to know the count again in order to find the critical t value. So whether you do it by, like I said before, just actually knowing the number of values in the set, or by using a count, it's really up to you. So t interval, it's the 2t one, so t dot inverse 2t. We want 0.10 comma count and same deal. A lot of going back and forth here. That'll give us our critical value, which I can now copy. I can put it here, making my 0.1 into a 0.05, and making my 0.05 or my 0.1 into a 0.01. All right, so I got my critical values. The low bound equals the mean of the sample means minus the critical value times the standard error. Same deal, but now with a plus. All right, so this is my low and high bound. I realized belatedly that I did not leave enough room for a conclusion, so let me do that here and here. So with 90% confidence, the high temperature will be between these two numbers. All right, so we are 95% confident that the population mean high temperature is between those two numbers, and it's degrees Fahrenheit, so about 44.17 and 56.47 degrees Fahrenheit. All right. Now I can clip this. I can, if I want to do a format wrapping, let it wrap. It looks kind of funky that way, but if I do a merge, it cleans it up nicely. So that's probably the way to go. And if you feel like this is a little too close to the second variable, you can add a column. And you just got to clean up some of the formatting, but it's not the end of the world. Okay. So then we do the same thing, but if we referenced everything the right way, so we want to reference these two values, C5 and 6, repeatedly. So let's get dollar signs on those. All right, leave the reference to B9 as a flex, so it can change as we move. So then pop it in, double check your references, pointing to the right thing, we're good. Do the same thing, pointing to the right thing, or things, so we're good there. All right, conclusion, generally the same. Never pasted it in here, so let's get that. But this time, instead of 44.17, 42.98. And 57.66. All right, then one more. This one 40.6. Uh, 64, right? And 59.998. So it's really just about 60. So I'll say 60.0. Right? Because the 7 makes the 8 round up, makes the 9 round up. So there we are. Right? And so now we're just going to do all the same stuff again, just for the second variable. Now, everything that we just did was in column B of all data. Now we're looking at column C. I'm going to throw a little bold on this, make it stand out a little bit. All right, so you see B here, it's going to go to C. So we're going to copy, well, really copy everything over. So what you could do, you know, it's kind of defeats the purpose of having it done over here. But if you really want to try to save some time, copy the whole shebang over, and then just change your references. It says G here, but we need it to be C. Yeah, a little on the tedious side there, but at least the row references are the way they should be. This should be pointing to the right thing. We still want C. All right, this is good. This didn't, well, yeah, change. I was going to say this didn't depend on anything, but you can see there. Let's see. Pointing to the right stuff. Not C5 and 6 anymore. This time it's H. All right. Then once we edit these, maybe you just copy these over like we did before. All right. So we'll go. Make sure it's pointing to the right stuff. It is. Pointing to the right stuff. It is. Got to change off my conclusions. This is now 30.12. and 38.50. Alright, still change this to C's. While I'm at it, I'll do this one. Alright, conclusion here is 29.31. Oops. And 39.32. And then the conclusion for this, 27.71. All referencing the same data, so or the same types of data, so I don't have to worry about units or anything like that. 40.91. All right, and so what this tells me is for the days that were surveyed, we're looking at a high temperature that's somewhere on average in the 40 to 60 degree range, and on the low end between the 30 to 40 and maybe 25 to 40 degree range. All right, so it gives us a sense of the center for each column of data. And so that addresses the confidence intervals for means with sigma unknown. So that takes care of each individual data set. Now we have to look in between the data sets. And for that, depending on what kind of data you have, you might have to do only one of these, you might have to do two of them, but you won't have to do all three of them because two of them conflict with each other. All right, so let me get rid of this. This is done. So is it match pairs? And I'll show you how to do it for all of them, but if it's not relevant, you wouldn't need to include it in your project, right? So the question, is it match pairs as in paired data? So going back to this, is it a before and after kind of a situation, right? Does one cause the other to happen? That's another way to think of paired data. And sometimes you don't know, all right? But what we did earlier, we determined some summary statistics. We got the median, the standard deviation, and all that good stuff. One of the things that we found was the sum of the variances, and we drew a conclusion based off of that of whether the data was likely independent or dependent, right? And so whatever this says here dictates what you got to do, all right? So if you think, so let me start with the dependent, independent. If it's independent, if it says likely independent, then what you would do is you would just jump right to independent samples and follow these procedures. If it says, like it says here, likely dependent, you have to ask yourself, is it the case that one variable possibly caused the other to happen, in which case it would be a correlation situation, or is it the case that it's a before and after, right? Paired data, one measurement, one individual, two measurements taken. Mine looks like paired data, all right? I mean, when you're talking about high temperatures are usually daytime temperatures, and low temperatures generally overnight. So before and after what? Before and after sunrise, maybe, right? So I can make a case for that. I could also make a case that a high temperature, a daily high temperature, could cause an increase in a daily low temperature, right? Now it's kind of a give and take relationship, because you can go the other way and say, well, the daily low temperature caused a change in the daily high temperature. But if you can look at a causal impact, then that would be a case for you to use a correlation. So if you're confused, you probably want to do both, right? But what I'll do is I'll first show you how to handle the independent scenario, all right? So again, mine says likely dependent, so I'm not working with independent data necessarily, but I'll show you anyway, all right? So in my confidence intervals, I'm going to go for my independent samples. I'm going to pull that. And I'm going to put it over here. Now, my spreadsheet's going to be pretty wide when I'm done with it for confidence intervals, but remember, you're really only going to have one of these. So it's going to be the within each data set, the confidence intervals, and then between the two. All right. So whether it's independent, as in what I'm doing here, or dependent, as in match pairs, or dependent, as in correlation, one way or another, it's just going to be one additional confidence interval associated with this. All right. So let me grab my structure, I guess. This talks about algebra and things like that, but really doesn't matter because I could just change the context. And again, in terms of the formatting for readability, it's nice to have something consistent. All right, so this is high, this is low. All right, we do need the actual counts now. So high, just make a little note here, the high end and the low end. And those values I'll just type in. In terms of consistency, generally it's okay. I might change a little bit of the formatting here, like for example this. I don't really love it, so I'll go alignment, wrapping, and I'll wrap it and then do the merge. You know, just to make it look a little bit more consistent. But it is a different confidence interval, so it's not going to be precisely the same. Now we do have the sample means and sample standard deviations for the highs and lows, which I realized belatedly that I did not label over here. So I'm going to put high temp, low temp. I'll bold those two. So I could just pull this information. I don't have to go back to the main spreadsheet, or the first tab, I should say. Right, so we got that. Autofill, I think I'll take that because that's right, yep. Then we'll do the same thing, equals this. Every now and then the suggested autofill is exactly what we need. The difference in sample means, so equals high minus low. The standard error, if you go back to the assignment, actually it might be somewhere, I guess. Well, you could pull it from here, but it's really, it's a formula that for whatever reason I didn't paste in here, but I could just dictate it, right? So it's equal to the square root of, we're taking the mean, squaring it, dividing it by the number of, sorry, not the mean, apologies, the sample standard deviation squared to make it a variance, dividing it by, and this is what I said before, we would need the count. So let me actually pause here for a minute, like not literally pause, but let me do a count. Equals count, and let's go into, there's an equal number of values in each column, so I could just pull it from one and I'll have them both. 183. So just make a little note there, 183. And it's the same for low. For independent samples, it doesn't always have to be the same, so that's why we allow for differences there. All right, so let's try standard error again. Equals SQRT. We're going to take sample standard deviation, square it, divide it by 183. Add to it the other sample standard deviation, squared, also divided by 183. And we get an error, of course, because why wouldn't we? Let's see. Got an extra equal sign there? What's going on? No? L4. I didn't put the power of 2 in there. Look at that. So now I got my standard error. My confidence level, I'm getting pretty much the same way that I did before. Normally we would take the smaller value and divide it by, the smaller value and subtract 1, the smaller n value, but they're the same, so it doesn't matter. And these n values are the same as these n values, so this is actually going to be exactly the same. All right, so I can just take this, pop it over, and that'll be the same for you because that's how I designed the assignment. All right, for you to be able to do that. All right, so to have those two equivalent n values. All right, same idea here. Just pop it in. This time it's 0.05. And this time it's 0.01. All right, so we got that, and then our low and high bounds. Similar idea as what we did before. The low bound. This time we're looking at the difference in sample means minus my confidence. The critical value multiplied by the standard error. All right, get some dollar signs on the m's. L we're going to leave flexible. I feel like if you come out of this course at least being comfortable with why and when you use dollar signs, that's a good skill to have. All right, make sure we're pointing at the right stuff. That, and I feel like I say that a lot, make sure you're pointing at the right stuff. That's another useful skill. And just being careful about those row and column references. For this one, when I pasted it over, it had that concatenate feature going. All right, so mean difference in temperature. So, yep, is between those two numbers. Not points anymore. So I'll just put degrees in there once. We're 90% confident that the population mean difference in temperature is between this and that degrees. Fix my spacing there. And if you do a nice job concatenating, then there's a reward in it, is that it's going to make the adjustments as you go. All right. I got some extra yellow here that I don't really want. That might not be the case for you. Just anytime you notice something doesn't look great, take steps to clean it up and things will go well. All right. It's all about presentation at this point. Now, both of these bounds are positive. All right. So that means group 1 is greater than group 2. All right. So group 1 represents the high temperature. So on average, the high temperature is greater than the low temperature. Now, I'll go back to what I was saying before. We really shouldn't be using this particular confidence interval for this type of data. All right, they're not independent samples, it's paired data. But I did it just to show you how to go about doing an independent samples confidence interval for the daily data final project. Right, so it's more academic than anything else, because when I go through all of this and I draw the conclusion that, oh gee, look, my high temperatures on average are greater than my low temperatures. High temperature as in the temperature around noon, maybe 2 o'clock in the afternoon versus like 2 a.m. Yeah, daylight temperatures are typically warmer than nighttime temperatures. we're not reinventing anything here. That's not earth-shattering in terms of a conclusion, right? So just understand that I just did this to demonstrate what you would do if in your set you were looking at likely independent data. I have likely dependent, so I would do a confidence interval for the difference in high and low temperature. So in my column E, one of the reasons why I had you leave a little space here for column E is to put difference in there. And so we would take my high temperature, subtract from it my low temperature. Suggested autofill looks good. So I'm going to do a one population confidence interval on the difference in data points. All right, so for that I could do one of two things. So I'm done with this assignment now. See, I'm just ticking them off as we go. That one we're not at yet. I could do it this way and just pull all this information over from the match pairs confidence interval. But if you look at it and compare it to what we did for the one population, right? So all of this, so high temperature, low temperature, has the same structure as the match pairs design, right? Sample mean difference, sample standard deviation of differences, mean of the sample mean, standard error, and so on. But everything else after that is pretty much the same. I could either just take what I have here and copy it over, make some adjustments, or, if you're more comfortable doing it this way, you can take all this stuff and bring it over. You really have the option one way or the other. So this would be match pairs. And then I could just pop in my information here, just like we did before. All right. Now, notice the font size difference. I don't know, maybe we want to be consistent there. So let's make it all 10. Keep this bold because it's the title. Sample mean difference, so equals average. Go into my all data. I'm looking at my difference column now. Sample standard deviation, so all data, same references, mean of the sample means equals this, standard error equals this divided by the square root of however many values. We used count before, but then later on we found out that there were 183 values. And just a note on that, for yours, you should have much, much less, right? So somewhere in the neighborhood of 40 to 50 values, right? I have 183, so we're locked in there. I could pull over my calculations. All right. Oh, I wanted to click in and paste it. Oh, that's not what I wanted to do. I must have copied the wrong thing. Hang on one second. There we go. So bring it in. Close this up so I can see. All right. Yep. Same idea, so just right on down the line. I'll just do it the way I did before. Oops. Copy, bring it in, change point 1 to 05, and then change point 1 to 0.01. Get our bounds equals the mean of the sampling means minus critical value times standard error. Dollar signs where necessary. Oops, no, that's not where it's necessary. Okay. Bring this over. Conclusion writing for match pairs is very similar to independent samples because we are talking about the mean difference. So I'll do that. Let's free it up here, clean it up. Get rid of some of the extra fluff here. Yeah, anytime you go from one spreadsheet to another, you deal with a little bit of that. All right, it's pointing to the right stuff. That's the question. It looks, yes, it does. All right, so we're 90% confident that the population mean difference in temperature is between 14.049 and 17.961. That matches what I have for my intervals. Oh, I guess I can't do that over a merge, so I'll just leave that be. This one I might be able to do. I guess not. Okay, so I'll just leave it alone. You can't have everything. So they're both positive. So we're looking at, again, an instance where the first group is more than the second group. Right? We can do the same thing here that we did before. Just copy, paste. Copy my conclusion. Pointing to the right stuff. Free it up and clean it up. Alright, same idea. Just pull this up a little bit. Both bounds are positive, so we're looking at over highlighting here. It's just this one that I need, so I can do this also. Alright, it's the same idea. I'm going to get a little greedy here. Probably not going to let me do it. Oh, let me do it. Great. Alright, so for that highlighting, again, this is just all to make it look a little nicer. Both bounds are still positive. So on average, the high temperature is greater than the low temperature. Yeah, that's true. In all three cases, we showed that the high temperature is greater than the low temperature. All right, so again, not really learning anything too special about what's going on here, because the most appropriate one for my type of data is actually not an independent samples. Again, that was just to show you how to do it. It turned out it was not matched pairs either, because again, we're not really learning anything. Of course, the high temperature is going to be greater than the low temperature on average, right? Unless you were talking about two different locations. Like if you had the daily high temperature in Alaska versus the daily low temperature in Nevada, you know, maybe you can draw the opposite conclusion, although desert areas get very cold at night, so who knows. But yeah, so that only leaves us one last possibility, which is the linear correlation case. So I'm going to grab all of this from the linear correlation confidence interval. And again, this seems like a lot, but I'm showing you how to do all three possibilities. You only need the one that makes sense for your data. All right. So this is linear correlation. Pop this stuff in there. All right. It's not rating versus price. That was from the assignment. This is low versus high. We tend to go with the y variable first and then the x variable. It actually doesn't matter in this case which one is the y and which one is the x, but we tend to do it, whatever the second column is, we think of as the y. So I'm going to do my line est. I'm going to grab my paired data. Comma, true, comma, true. Ref. Mismatch range. What did I do wrong? What did I do wrong? Oh, rookie mistake. So we actually don't do them all in one shot. And that I actually knew. I just brain cramped there. Sorry. I don't even think I'm going to edit that out of the final video here. I'm going to own that mistake. All right, so column C versus column B. Because, every time we work with like scatter plots and stuff, we usually copy the entire table and then let Excel do the work. But here, it's slightly different. So it's worth actually making that mistake so that you see it in action. All right, so there we go. You might remember we only need these two entries here. Confidence level, same idea as before, except now it's -2 from the count. All right, so let's see here. Oh, there's another mistake. I never subtracted 1. Oh boy, that's a big one. So we got to go through, change them all. I'd love to say I made that one on purpose to see if you were paying attention, but unfortunately that is not the case. I'll try to make a note of it in the description for the video that this mistake is caught later on, so that maybe you can avoid it early on, but yeah, because otherwise I'd have to change the whole video, and that, it's no good for anyone. I mean, mostly me. Full disclosure, I'm making this video sitting in a parking lot in the middle of Stamford, Connecticut. So yeah, I was trying to be efficient, and in doing so, I made a mistake, and it happens. All right, so this time, confidence level, same ingredients, just -2 instead of -1. And the -2 because we're dealing with 2 variables. All right, so equals this, -2, and not really much of a difference. I'm just double checking. Actually, no difference at all in terms of what it rounds to, and that's because, just making sure. Yep, and that's because the data set is so large that once it gets to a certain size, there really is no distinction. Right? It rounds to essentially the same value. All right. But in terms of the low bound and the upper bound, it's equal to whatever my slope coefficient is minus my critical value times my standard error for the slope. All right. Same idea, just with a plus. I'll give the dollar signs on this one. I meant to do it on the other one already, but I botched that already, so I'll fix this here, and then I'll go back and grab it here. All right, so then we are 90% confident that the population slope between low and high temp is between 0.692 and 0.806. And like I said, for format, we like to wrap it. Looks a little nicer. If you want to break up the merge here, you can. I think it's fine as it is. This one goes to 0.05. My low and high bounds, if I $signed it up the right way, it should point to the right stuff. It indeed does, so we're good there. All right, do this again. Go to a 0.01. Do that. All right, grab my conclusion, make any necessary edits. This one is now 680, 817. Six, 5, 9. I'll leave the 5, 9. I'll go 3 decimal places. And 839. All right. If 0 is in the interval, there's no significant linear correlation between the variables. Well, 0 is not in the interval. Also, I noticed the font size again. So let me just adjust, go down and up, and it changes everything. All right. So we're 90. No, we're sometimes not 90. This one is, my first one was 90, then the second one was 95. Change this. And the last one, this one looks all right, so 99. All right. So with confidence, there is a significant linear correlation between the variables. So there is a significant all right. Now, a slope represents the change in y over change in x. So change in low temperature per unit of change in high temperature. All right. So somewhere, I'll say there is a slope somewhere between, what's the lowest of the low here? Let's say, yeah, about 0.65-ish to about 0.84. So 0.65 to, I'll say 0.85 units of change in high temperature per unit of change in low temperature. Per unit, so actually it's the other way around. Low temperature, the y variable comes first. So per unit in high temperature. All right, so that means that for any change in, any unit of change in temperature for on the high end, all right, let me just clean this up a little bit. All right, so for every unit of change in temperature on the high end, there will be anywhere from about 0.65 to 0.85 degrees of temperature change on the low end. Right? So if, let's say the daily high temperature was 80 degrees, right? The daily, and then increased by 1, then the low temperature would increase by somewhere between 0.65 or 0.85 of a degree. All right. So it's useful information, but it does take a little while to kind of wrap your head around. All right. But these are all the different confidence intervals that you can have in your final project. The first two have to be there. Out of the three remaining, the independent samples, match pairs, or linear correlation, you use only the one that makes sense based off your data. And if you're not sure about that, you can ask me.